Welcome to the lecture 2.4 on symmetry for college algebra. Like this image of me? Ooh, symmetry. Pretty fancy. Okay. Today's pause is talking about reflection. We just recently had a test on chapter 1, and so it's always good to kind of pause a moment after any kind of milestone or project, etc., and kind of do a little bit of reflection. It's always good in our life to take moments to reflect back on what we want, and what we're doing to get there, what's happened well, what hasn't. So I've got a few quotes here for you. Reflection, looking back so that the view looking forward is even clearer. Taking a moment of pause. This is from John Dewey, the father of modern education. We do not learn from experience, we learn from reflecting on experience. So, there's another quote that says something like, failure isn't failure unless you don't learn the lesson. And I think that's what this quote kind of speaks to me. Without reflection, we go blindly on our way, creating more unintended consequences and failing to achieve anything useful. Again, a very similar idea that if I keep doing the same things and having the same result, which is not what I want, if I don't ever reflect on that and change what I'm doing, then I'm going to get the same things. In some recovery programs, they talk about the definition of insanity is doing the same thing and expecting a different result. And part of that's about making choices, but it's also about reflecting on them. I think I've already shared this with you probably by now, but a great and simple tool that I use often, I use it at work, I use it in my personal life, etc., is what I call rock sucks missing. And I can use this about anything I'm doing, anything I'm working on. I can use it in a team. It's just a quick way to kind of get to some core things. And I'm just asking 3 simple questions about any project or about what's going on. So here in the course, you might ask, first of all, what rocks? What are you doing that's helping you be successful in this class? What did you do in the class up until the first tests that helped you do better? The second question is what sucks? What did you do that was kind of hurting you, that didn't help you succeed? Did you use the helps too much? Did you not go back and do another problem, etc.? And then the last question is what's missing? And this is about, like, if you could think of adding something you didn't do, but if you did do something, an external resource, etc., what's missing? What could you add to make things better? So again, another little pause to kind of go a little bit deeper before we head into the lecture. Today we're looking at symmetry, and it's really talking about graphs and whether a graph is symmetric with respect to the x-axis, the y-axis, and the origin. Depending upon the symmetry, a function is then called either an even function, an odd function, or neither. Okay? So let's look at the tests for symmetry. So for x-axis, we are going to replace the y. This is an algebraic test, so we're talking about the equation, not the graph, but this is a x-axis symmetry. You can see that it's the same on both sides of the x-axis. When we're looking at the equation, to see if it is, without looking at the graph, we replace every y with a negative y, and if it produces an equivalent equation, then the graph is symmetric with respect to the x-axis. And that sort of makes sense. Like, for example, here at x equals 2, if you go up, you can see the y value, the positive y value, is the same as the negative y value. So every x has a positive and negative y, and that's why we do this. For the y-axis symmetry, and here's a graph here, we can see it's kind of very similar. We can see that it's reflected across y. It's the same on both sides of y. With the equation, we replace the x with a negative x, and if we get the same equivalent equation as the beginning, then the graph is symmetric with respect to the y-axis. And again, we see the same thing here. If we go up to where y equals 3, we can see we have a negative x value for that y value, and we have a positive x value for that y value. When we're talking about the origin, this is reflected around the origin. This is not always easy to see, but what we have here is if we replace x with negative x and y with negative y, and we have the same equation, then the graph is symmetric around the with respect to the origin. And so if you look at this point at -1, we have -1 for x and a +1 for y. And if you change both of those values, x becomes positive and y becomes negative. We have the same thing. As far as visually, what you're trying to do here is if you have a graph and you're not quite sure, rotate it 180 degrees. And if the graph looks pretty much the same, if the graph looks the same, then it is symmetrical to the origin. So the origin symmetry is if you can rotate the graph 180 degrees and you have the same shape, then you have origin symmetry. So let's look at how this is done with an equation. Test y equals x squared plus 2 for symmetry with respect to the x-axis, the y-axis, and the origin. So let's take the x-axis first. Now, these are pretty easy to remember, although they are counterintuitive. When we're testing the x-axis symmetry, we replace y with negative y. So we replace the opposite variable. So we take the original equation, and wherever we have a y, we now put in a negative y. Okay? Now what we want to do is solve this so that we have the left side of the equation the same. We want the y to be positive. So if we multiply both sides of the equation by -1, we get y equals negative x squared minus 2. So now we see the left side is exactly the same, and we check the right side. X squared plus 2, negative x squared minus 2. These are not the same. Since this equation is not equivalent to the original equation, so it's not symmetrical to the x-axis. It's not x-axis symmetry. So now let's do the y-axis. And in the y-axis, we're going to replace the x with negative x. Okay? When something is happening to that variable, for example here, x is being squared, then whenever we put the negative x or the negative variable in, we want to put it in parentheses. Okay? Because it's x squared, and now we want negative x squared, which is very different if we didn't have the parentheses. Well, negative x times a negative x is a positive x, so we get y equals x squared plus 2. We now compare this back to the original equation, and we can see that it is the same as the original equation, so this is symmetrical to the y-axis. Okay? For the origin, we replace both x and y, okay? So wherever we have a y, we place a negative y. Wherever we have an x, we have a negative x. If anything's being done to that variable, we put it in parentheses, and then we simplify. Well, negative x squared, we're going to get rid of that parenthesis first. It's negative x times negative x. That's a positive x, so positive x squared. And then we have negative y on the left. We want to make that a positive y, so we multiply both sides by -1, and we get negative x squared minus 2, which is not the same as the original equation you can see at the top. So again, since it's not equivalent to the original, so it's not symmetric to the origin. Here we can see the graph here, and you can see that it is indeed symmetrical with respect to the y-axis. And what does that mean? It's the same on both sides of the y-axis. It cuts it right in half, if you will, like an apple. Okay, so these tests are not very difficult. The rules are not hard to remember, except they are opposite. Again, x-axis, you replace y with negative y. Y-axis, you replace x with negative x. And for the origin, you replace both. So now let's talk about even and odd functions. This is just a connection with that same concept. If a graph of a function f is symmetric with respect to the y-axis, so it's y-axis symmetry, we say it is even. Okay, it is an even function. That is, for each x in the domain of f of x equals f of negative x. This is just functional notation. Again, it's saying replace x with negative x, and if they're the same, then we do have an even function. If a graph of a function f is symmetric with respect to the origin, we say that it is an odd function, okay? This is an easy way to remember these. Odd begins with O, origin begins with O. So odd functions are origin symmetric, and that means that, and this is the math language, that is for each x in the domain of f of negative x equals negative f of x. Now remember, we replaced x with negative x, and we replaced y, remember f of x is y, with negative y. So that's this notation language. Okay, and again, remember that an origin graph simply means that you can rotate it at 180 degrees and you'll see the same shape. So let's do a problem. Determine whether the function is even, odd, or neither. H of x equals x to the fourth minus 4x squared. Of course, remember that this is the same as y equals x to the fourth minus 4x squared. Remember that even is y-axis symmetry, so that's what we're going to check for. We're going to replace x with negative x. We take our original equation, and wherever there's an x, we replace it with negative x in parentheses. Negative times negative times negative times negative is going to be positive, so we're going to have positive x to the fourth. Negative x squared is negative times negative, so that's going to be positive, and we're back to the original equation. Since it is equivalent to the original equation, we do have symmetry with respect to the y-axis, so this is indeed an even function. This is indeed an even function. Now, because we've already noted that it's even, we can stop. It is not possible, just like with a number, for it to be even and odd, okay? It's either even, it's either or odd, or it's neither. Since we know it's even, we're done. However, I want to show you the test for odd. Remember, odd symmetry is to replace both variables with negatives. So wherever there's a y, replace it with a negative. Wherever there's an x, we replace it with a negative. Wherever something's being done, the second x is being multiplied by 4 and squared, we replace that variable inside of parentheses. We've already seen that the x's will become positive because the exponents are even. And then if we multiply both sides by -1, we get y equals negative x to the fourth plus 4x squared, which indeed is not the same as the original. It's not equivalent to the original. It's not symmetric to the origin. It is not an odd function. Here's the graph. You can see quite clearly that it is an even function, that it is a y-symmetrical function. And this is how we would say it in notation. We see that h of x equals h of negative x. When we plugged in the negative x, we got the same function, okay? So thus h is even. This function h is even. I just wanted you to see the notation because you'll probably come across it in your homework assignment. So a quick question, and then I'm going to let you go. We've done a really short lecture today. Why is there no function designation, like even or odd, for x-axis symmetry? Do you know? When you look at this, does this help? What have you learned about functions? Do you remember the vertical line test? X-axis symmetry, by its definition, can never be a function because you're going to have at least 2 points on 2 y's for every x. You're going to have 2 points on every vertical line, so it cannot be a function. Great lecture. Good job. Good luck with your homework. Reach out if you need me.